Hello everybody and welcome to day 4 with Lean Prover. I am once again not a professional and not liable for any test that you might fail or any proofs that you might garble, but we're going to try to get into it. Today I think we're going to talk about conjunction. Last time we looked at true and false and tactics, but I think we can keep going on. So let's go ahead and give it a shot. So conjunction. So if we have a proposition that P is true and we know that a different proposition Q is true, then P and Q should also be true. Like, that makes sense, right? So if we have, let's just go ahead and put this into comments. If we know that P is true, we know that Q is true, that means just intuitively that P and Q is true, right? Now, if we want to put this into more mathy terms, we could also just write it symbolically as P and, so you do backslash A and D, see if there's any other ways to do it, and wedge. Okay, backslash wedge also works. Cool. And Q, this is basically just a true statement. And that makes sense, right? P and then and Q. It's basically like just saying like true and true, right? And that should obviously go as true. I think we looked at that in day 1, because we technically didn't, but it's that same sort of principle. So today we're going to look at an and.intro. And so let's go ahead and check what and.intro does. So and.intro says that with an A and a B, well, I guess more like P and Q after your M1 and M2, you can make that M1 and M2. These are just basically two different propositions. So let's write this out. Just maybe it'd make a bit more sense if we do, if you're still a bit confused. So we're going to use the curly braces again. We explained that in the last video, why. So we have P and Q, and they're both propositions. And basically we're going to have a proof of P, all right, and a proof of Q. Because if we haven't proved them, then we're just taking things for granted at that point. And what do we want out of this? We want that with P and Q, we get that P and Q, right? And what is this? This is just and.intro. Fantastic. How can we use it? All right, so let's define a couple things first. We're going to define P as, let's just say 0 equals 0. We've been doing that a lot, so we're going to go ahead and bind it there. Let's go ahead and check that to make sure it's exactly what we want. Yep, P is of type prop. If we want to be like really specific, you could also just do like Q is a proposition. We're going to bind it to 1 equals 1, not 1, 0, 1. And I'll do the same thing, but Lean can infer that this is a proposition. So this isn't really necessary, but if you really want to have it in there, you should just go for it, honestly. So let's get out two lemmas. First is going to be our proof of P. Let's just do PFP. I don't really want to write out proof. And that's going to be P. And how are we going to bind it? We're going to bind it using .ruffle of 0. Or let's go ahead and do the same thing for Q. Just we got to remember that Q is 1, right? So then we got to do 1 instead. Otherwise, Lean will scream at us. All right, so this is all great, but how would we want to define a proposition with an and conjunction, right? So let's do a definition. Let's call it P and Q. Looks like pand Q. It's like fake panda, but it's pan Q. All right. Anyway, P and Q. Let's do the same syntax, just so we know that it's a proposition. And this is going to be P and Q. Lean doesn't yell at us, which is always good. Let's just go ahead and check that. Perfect. It's a proposition. It's exactly what we want. Now what we could also do is we could also like check it directly, but it should give us just the same result. Yep, just a proposition. That's all we were looking for. So now we really got to throw in our and introduction rule, right? So to put this more into like Lean terms, this is like more of an easy read terms. Remember that we need the parentheses because these are proofs, right? And this is again what we're trying to do. We are trying to form basically just a proof of PQ. And that's what our and.intro is really going to do for us. So let's see if we can get this to work. So let's make a theorem. It's going to be a proof of PQ. And we want P and Q, right? This is what we were looking for. So how are we going to bind it? Well, we just declared that we are going to try out and.intro. So let's see what we can get out of it. And.intro, and we need two different things. So we're going to need basically two propositions. So we have a proof of P. That's going to be our first one, because we notice from here that A is the first one, B is the second one. So if we mix that up, it's not going to be a good time. There we go. So like if we tried to like do this, and you'd be like, wait, I'm type checking you, and I'm like, your Q is not P, or proof of Q isn't applicable to P. And the same thing here. You can't just do that, right? So things do need to match up in Lean. And I suggest you study this one pretty well, because it's going to pop up a lot as we move on. So I would highly recommend that you keep that in mind. It's a pretty good one, in my opinion. So how about we try this with a tactic state, right? That'd be pretty cool. I mean, I guess that depends on your definition of cool, but let's just go ahead and make a new theorem. It's basically going to be the same thing. But this time, we're going to use a tactic. Okay? So what do we need for a tactic, right? We need a begin and an end. And now, our goal is to try to figure out what to put in. Once again, to open up the tactic message panel window, I don't really know what to Control-Shift-Enter, that pops up. And what do we need? We need to prove this. We need to prove P and Q. So how are we going to do that? Now, there are a couple ways we can do this. One of them is to split it up and prove each of them separately. All right? Because Lido can just put this back together. So what about we just apply and.intro. Don't forget the comma, because we're going to be doing more things later. So what do we have now? We applied and.intro, which tore this apart, and now we have two goals. One is to prove P, one is to prove Q. But we can do that very easily, right? So remember, when we're trying to like pull things out, we need to exact, right? So what are we going to be exacting? We need a proof of P. P is 0 equals 0. So we can just exact eq.refl 0. Now, at this point we have two goals. Let's look at our end again. Uh-oh, tactic state is still Q. So what happened was we did get P. But now we just need Q. So how would you do Q? Right, so what we need to do is we need to exact the same sort of thing, but for 1. Because that'll give you Q. I'm not sure if you can do 0, 1, 0. Nope. So we're going to apply it directly to each one. So we do 0 first, then 1. There we go. And if we want to just go ahead and check this. Perfect. That's exactly what we're looking for. It's not using sorry anymore. So I believe you can also do split. Don't quote me on this. Yes. So split's going to basically do the same thing. I kind of like split a bit more just because I feel like it makes more sense. Just because like, oh, I have P and Q. I need to split it apart. Do P and then Q. But I think mathematically, and apply and.intro just seems better. I don't really know. But basically that is what we're gonna do there. So we can do it in a different way as well. So before we, let's see, I believe it was here, right? So we had that other way of doing it. We could also do like a have exact, right? So have is basically we're just going to define new things. So, you know, let's go ahead and try that. You can try it on your own first, but I'm going to do it out just right here as well. Oof. All right, so here's what we've got. We need to prove that of P and Q. So let's have A, and we're going to bind it to dot refl of 0. Have B, bind it to eq.refl of 1. Don't forget the commas, I always do. And now we have these two cool things. So here we've defined A 0 equals 0 and B is 1 and 1. We already know that P and Q are 0, 0, 1, and 1 already. So what we can do is we can just go ahead and apply and.intro to A and then B. And what has that done? That's basically just given us what the equivalent of P and Q is, and lean is perfectly happy. We can go ahead and check that. Fantastic. And we're not getting a sorry, so that means we pretty much did it correctly. Now the nice thing about this is you can actually just do it in any order. So like if I had B1 and A0, right? Because it's like already here, you don't have to like, oh, I don't know what's going on, it's not in order. With this one, because this is your first, that's your second. In this case, you just need the first here and then the second there. So it can be A and B, right? Perfect. So that's how you can really start using tactics to your advantage. Because now it's kind of easier to see what's going on, right? Right? It's not just more of this. You can really start putting more things just in the tactic. So we know how to introduce ands, but how about we like start eliminating things? So we're gonna try to eliminate something that's on the left side of the and something that's on the right side of the and. Sound good? All right. So let's go ahead and see what that would look like just more in a mathematical context. So if you have a P and a Q and they're propositions, and you have, let's say, a proof of P, I'm gonna call it just, I don't know, P and Q, right? Such there's our proof. What are we trying to get out of this? Doesn't really matter which one we do first, so let's just say we want a proof of P, and we are going to call that and.left. Now, I'm going to tell you guys right now, you can also just do and.left because it's just used so much that the developers, I guess, decided, man, I feel really bad for all the people that write 5 extra characters. Let's just take them out. You can just do and.left. It's a lot easier in my opinion. I mean, sometimes it's nice to have the elem. It's like, eliminate the left, but you know, it's up to you really. And then what about the right? So let's just go ahead and do the right as well. And what do we want out of this? We want proof of Q. And that is going to be our and.lem right and.right. Perfect. So we're going to implement these two things. So let's go ahead and check them. So we can see right here that for something A and a proposition B, right? Proposition A, proposition B, it'll return the proposition that's on the left, because that's where A is. If we switch this to right, it returns B, the one on the right. So it does make sense in that case. So it's not you're eliminating the one on the right, you're eliminating and keeping the one on the right, if that makes sense. Hopefully it does make sense. So let's try to apply these. We're going to go ahead and switch back to left. We're going to add let's just add another elem right. Actually, I will prove to you that right works. And we're going to put in our proofs. Whoops. All right. So what would we get when we check these? P makes sense. We can even see it here. We're gonna get a P, and Q, we're gonna get a Q. So I think that's pretty intuitive, right? So how else could we, go ahead and do this? So we can make basically just theorems out of them. We can say that theorem proof of P, given that we have like a proof of PQ, we can just do let's do and.left, the proof of PQ. Oof, what did I do here? Whoops. Actually, yeah, there we go. My bad. So that obviously works pretty well. And we can do the exact same thing. Remember that if we don't do anything, it'll just use sorry. And there we go. Lean is super happy. Now we can also do this in scripts. Well, not scripts, tactics, my bad. They're script based, So we have theorem. We're just gonna keep adding primes or whatever you want to call them. Begin. And we can just jump straight to the exact, honestly. So what has that done? Basically, once this is evaluated, we end up with a P. P is what we're looking for. It pulls it out. So it's right here. It doesn't really pull it out. That's a very bad way of explaining it, I guess. But basically, it just shows, here's what we were looking for. Let's take it. The other way we could do it is using the halves. So we have our proof of P. And we're going to basically do the same thing as the exact before. And then we're going to exact that one. So basically this whole statement, you only need one statement. These are doing the exact same thing. One, we're just kind of defining a new object and then pulling that object. And this one, we just have the object and we're immediately pulling it. That's pretty much all it's really doing, I guess. All right. Whew. We have done a lot. I don't know, have we done a lot? Yeah. We've done quite a bit. All right, so what if we had something new? We've done P and Q, but what if we have something different? What if we have, I don't know, Q and P? Right, this is new. It's a proposition. Bind it to P. Oh my gosh. There we go. Here's our new proposition that we've defined and bound it to Q and P. Whoa. Or I guess now we, proved it with Q. You get the idea. Okay. So how do we want to use this? Or how can we prove it? Using our previous proof. That's what we're going for. So we have our proof. Where is it? Basically this right here, right? So this is what, let's just say this is what we're taking, and we want this, right? How can we do that? If you want to pause and try to figure out yourself, please feel free to. Otherwise, we're just going to go for it. Let's add a new theorem, proof of Qp, Q and P. How are we going to solve this? We need and.intro. And here, we're actually going to tear the previous proof apart and put it back together in the reverse order. That's our goal for this one. We're going to do and.right, pf, pq, and.left, proof of pq, and we've proven basically that pq is the same as, actually p and q is the same as q and p. So what did this do? This kept the right side of PQ, so which is Q, right? This kept the left side, which is P, and.intro took the Q and the P and pretty much anded them, and that's how we got this. Super simple, right? Not that bad, not that bad. All right, so let's move on. How else could we do this? Right, tactics. So if you want to try to tack this tactic it yourself, feel free. We're going to do it real quick right here. Remember, it always begins with begin. And here's what we can do. So we could do a split. Then we can go ahead and exact. Because when we look at it here, right here, so I guess it didn't really, oof. Oh, a lot of crazy errors up there. So we can just like end, that'll help it out. Guess not. All right, anyway, we know what we're looking for now, because once we've split it, we're looking for a Q, we're looking for a P. Actually, it tells us right here now. Our first goal is a Q, our second goal is a P. So let's try to get the Q first. And we know that it was basically just this right here. So we're gonna kind of cheat this, copy, paste, and now we have to get our second goal. Copy, paste. Did I do that right? Oh, forgot the comma. There we go. And yes, we've proven the same thing with a tactic. Now we can also use the have method. We're gonna do it just really quick right here. I'm not sure which you may have decided to do. Both are perfectly valid. I personally think the have one makes a bit more sense. It's probably just me though. Oops, forgot the comma. Told you guys, I always do that, you know? And we're going to apply and.intro pfq pfp. Whoops. Boom. There we go. So what do? We got a Q out of this. We got a P out of this. So we got QP, QP, Q and P, Q and P. Super simple, right? Maybe. I hope it is. So basically what we did was basically just, oh my god, I gotta stop using basically. Simply put, we just use like a commutative property, right? So essentially what we've done is that we're gonna write this out. I think it's super helpful. You guys should always do it. Proposition of P and Q. So we have a proof of P and Q. And what we're going to get out of it is a proof of Q and P. I'm sorry. Right. So it is and.comm. Basically just and commutes. So let's make our own first, and then you can basically, once you know how to do it, you can just use and.comm. Yeah, see, so we have A and B, and that swaps it to B and A. Super simple. So let's make a new definition out of this. Let's just call it and.comm. We're just going to put it as an underscore just so we can differentiate it. Remember that we need curly braces here. These are both propositions. We have a proof, P and Q. And we need a bind. And we can do this with just an and.intro. And it's essentially what we've done before. We had an and.right, and Q, and.left, P and Q. Now I've obviously messed this up somehow. Oh, did it? Is it? Oh, it's already a thing. Alright, 2 underscores. There we go. That was awkward. I was like, I thought I was new. Actually, it's probably the same thing. And.comm and underscore comm. I didn't know that. Okay, interesting. So now that we have that, we can just directly prove this ourselves, which is why definitions are so cool. We don't have to like go through dozens of steps just to get one proof. We can define it somewhere else and use it later. So we'll have a theorem of Q and P. And we're going to use that and double underscore comm proof of PQ. Is this already a thing? Whoops. All right. And there we go. Wow. We have just applied our converter, our commutative property. We've converted a proof of P and Q to a proof of Q and P. Wow. See, isn't that so cool? Nope. Alright, well, I'm sorry that it wasn't as fantastic as you might have expected, but having proved that, I think it's pretty important. So I suggest you try it with different things. You can try it with all sorts of different propositions. I suggest, like, we did, what, 2 sets of natural numbers I would suggest doing maybe a set of natural numbers and a boolean, or maybe a string, etc. But you should definitely try it out. I hope you found this helpful though. We've gone through a lot. This is just all commutative property, wasn't it? So we started with and.intro. How do you put true propositions together? How do we tear them apart? And how can we reverse them? So that's what we've gone through today. Again, I hope you find that helpful. Take it with a grain of salt. I am not a professional in Lean. I hope you all have a nice day.